this is based on some master's work I did last year at the University of Salford. And really what we wanted to look at was designing a synthesizer, looking at perceived tension and acoustic features of a signal. This sort of motivation for this was an interest in horror movies and sound design, and how horror movies can use sort of sound to elicit feelings of tension. So primarily what we looked at were this idea of, can synthesized tones be used to inform a feeling of perceived tension, and can we define sample tension from acoustic features? And acoustic features are just sort of characteristic components of a sound. Now, previous work, just to briefly give some context, in the related areas involves the valence arousal space being investigated, matching emotions to different samples. Different stimuli include soundtrack excerpts, recorded instruments, generated signals. So these were all used as a sort of springboard of ideas to do my own research off of. As I see at the moment, we've got 3 areas of interest, which I'll cover. We've got the creation of the synthesizer, which is just a very standard basic FM synthesis, the generation of the test samples, and then the online perceptual test, which was run online due to issues with COVID. So first of all, we've got the, this is what the synthesizer looks like. It was built in Max for Live, and it's fairly standard. It's got 1 carrier, 1 modulator, both sine waves with their own ADSRs, a 3-band EQ to the right, and then a ratio and brightness knob, which I would say is probably where most of the interest comes from in this synthesizer. Signal generation, that was done through MATLAB, Max for Live, and Open Sound Control. It was done automatically through essentially recording the desktop audio and sending signals through MATLAB to Max for Live, which allowed a total of 600 sounds to be generated, which I then had to comb through and reduce to 206. And just as a quick example, I thought I'd show some, essentially what happens when you change just the brightness. Let me just make sure I'm actually sharing my audio as well. There we go. So that's with the brightness down at 1. And then if we turn it up just past the halfway point, we can hear it's much less pleasant to listen to. I won't make you listen to the other 3, but as you can imagine, ratio increases the harmonic complexity, and brightness sort of works as a fader knob for any added harmonics at the end. It's also worth noting that all of the synthesizer patches use the same note value and length as an input. So now we can move on to the online test. And what we've got here is a Likert-scale study, which is essentially a reference test. They'll listen to 1 sample as a reference, and then the second generated sample, which they'll say, oh, is it more or less, or more or less tense, essentially. And there was 3 tests run, 50 samples in each test, and a total of 23 participants took part in the end. And I've got another example of just what a test question sounds like. So yeah, that's basically what people had to listen to, variations of those sounds 50 times for each test. So now that we've got the results in, we wanted to plot them out and see how the data looked. And these are plotted based on median sample rating, I believe. So as you can see in the top spread of data, it's quite narrow. It sticks between sort of, well, it never really goes below 3 or 2. And a lot of the time is around 4, 5, or 6. So we had a very narrow range of data. And it was decided that rescaling might be suitable in order to make better use of the full Likert scale. And that comes with its own downsides, because you're interpreting participants' results. You're interpreting what they think about the test. However, it was decided just the pros outweighed the cons. We also did Cronbach's alpha to basically make sure that the internal consistency was kept through rescaling the data. And as we can see on the right-hand side, the third test actually failed the minimal requirements for Cronbach's alpha. And as a result, any further analysis had test 3 results removed. Then afterwards, we could look into PCA, principal component analysis. This is very brief, but essentially the 2 prerequisite tests, Bartlett's test of sphericity and the KMO test, were run, and they both were fine. So the data was okay to be used in a principal component analysis. So here we've now got 2 graphs. We can see the percentage of variance on the right-hand side and the eigenvalues on the left. When looking at principal components, we want to extract as many useful principal components as possible. And this can be typically done through looking at the eigenvalues and using anything with an eigenvalue of 1 or greater than 1. However, I should note that on the left-hand side, the third principal component does actually have a value of about 0.98. And for some reason, this figure's rounded it up. So in the real data, we essentially have just the first 2 principal components being useful. And as we can see, the more principal components that are useful, the more variance that's explained in the model. So you want as many as possible, but 3 is very much a borderline case in this study. From here, we can also look at the loadings. We've also got the supplementary value of tension rating plotted on this graph. So we can see where tension rating fits compared to the other acoustic features that have been investigated. And as we can see, dimension 1 is largely shown by frequency-based features, whereas dimension 2, largely time-based features. And tension rating very heavily correlates to dimension 1 only, or dimension 1 specifically, it should be said, which is more frequency-based features. And this makes sense based on prior studies I've read, particularly spectral centroid and brightness seem to correlate highly. This is another graph which shows much of the same, just that dimension 1 has a greater effect on tension rating than dimension 2. And the data does seem to be spread somewhat randomly. It's hard to see much of a pattern there. So then finally, using all of this, we can put the 2 principal components into a linear regression model. Now, the linear regression adjusted R-squared and p-values were fine and usable. However, when looking at the assumptions, or the key assumptions of a linear regression model, we can see that homoscedasticity on the left and normality on the right were both breached, which makes the model not particularly useful. I mean, that red line on the left-hand graph, we would like to see flat. We wouldn't want to see any sort of patterns, and just everything about that graph on the left is incorrect to some degree. And that's where the research from last year left off. So when thinking about future work, at the moment, I think we're looking into biometric data, so galvanic skin response in particular, as there are so many problems with self-report methods, and it's better, I feel better to look into more objective measures than subjective. There's also issues around whether the PCA dimensional space is filled out enough with acoustic features or sufficiently filled out. And on top of looking at biometric data, I think switching to discrete data rather than continuous for the tension rating would probably yield some better results. But yeah, that's everything at the moment. If you have any questions.